All right, I think we can get started now. We have 38 attendees. Welcome, everyone. Good morning, or good afternoon, good evening, depending on where you are. Thank you so much for joining us today for Kenji Satake's webinar. Before we get started and I introduce today's speaker, I have a few announcements and housekeeping to share. I am Anaïs Ferro. I am the SD4D Managing Director, and I'll be your host today. First of all, we have applications to host an early career as part of our exchange program, and they will close next week on July 1. This is our fourth and final edition of the exchange program. If you are a scientist and you are based either in the US or in Chile, and you are interested in welcoming to your group a student or a postdoc for a 1 month visit, please visit the link in the chat that I'll post in a second. Application for participants will open on July 1, so please stay tuned, and I will share an email, an announcement on the SD4D listserv. A quick housekeeping now, this webinar is being recorded and will be posted later today or tomorrow on our YouTube channel, where you can find all our past webinars. Live translated captions are also available. You can select your preferred language by clicking on the closed captions button located at the bottom of your screen. If you have any questions for the speaker, feel free to use the Q&A feature, which is also available at the bottom of your screen, and we'll get to them at the end of the presentation. Okay, so I'm very happy to introduce today's speaker, Kenji Satake. Kenji, welcome.
Thank you.
Kenji Satake is a seismologist, professor at the Department of Earth Sciences at the National Central University in Taiwan, and professor emeritus at the University of Tokyo. His research focuses on giant earthquakes and tsunamis worldwide using geophysical, geological, and historical approaches. He developed a tsunami waveform inversion method that combines recorded tsunami data with computer simulations to reconstruct tsunami generation and propagation. His work also uses tsunami deposits and historical records to investigate past events, including the 1700 Cascadia earthquake and tsunami. Today, Kenji will discuss giant earthquakes and tsunamis in the world. Kenji, you have the floor.
Okay, thank you. Good morning. Well, this is in the morning in Asia, or good evening for those people in the US or Chile. Today, I'd like to review some giant earthquakes and tsunamis in the world. Okay, so let me start. Where do I start? Okay. Well, if you're a SSA member, Seismological Society member, you might have seen this. SSA, Seismological Society America, started open access journal, the Seismic Record, 2021, and recently they got the first impact factor 5.3, which is amazing. So congratulations for that. But the reason I'm showing this picture is this is a front cover of last October issue. And the SSA uses this for the advertisement of the TSR. But when I look at this picture, this looks old, but it shows some major earthquakes around the Pacific, around the Ring of Fire, and also some other size, severe earthquakes region in light shaded one. And I was curious how old it is and when this was made. So I asked them for the original. Then they showed me that this was 1935 map of earthquake zone in the world, compiled by Nicholas Heck of U.S. Coast and Geodetic Survey. It's amazing that in 1935, nearly, it's 90 years ago, they made this map and showing the major earthquakes around the Pacific Ocean, mostly subduction zones, and also the Middle Atlantic, and also from Europe to Himalaya. Okay, again, this is 1935, long before the plate tectonics or the conception of like a subduction zone. But the earthquake distribution is very similar to what we see today. So this is the map from I just downloaded 10 minutes ago from USGS website, and this is just a seismicity in the last day. And actually, in the last couple of hours this morning, well, my time, in the last couple of hours, uh, we had magnitude 7 earthquake near Venezuela and also in Japan this morning in my time. I really actually felt this earthquake this about 1.5 ago. So this is again the earthquake distribution of the earthquakes, but to quantify this, we need some measure for the quantification. By the way, we call this magnitude giant earthquakes for those earthquakes with magnitude 9 or larger. And for the magnitude 8 or larger, we call it great earthquakes. And magnitude 7 larger is for large earthquakes. So again, this morning we had 2 large earthquakes in Venezuela and Tohoku. But the question is, which magnitude scale would we use? Okay. And probably most of us know that, most of you know that we use a moment magnitude scale invented by Professor Hiro Kanamori back in 1977, nearly half century ago. And the moment magnitude scale is based on seismic moment using this formula. And using this moment magnitude scale, like a 1960 Chilean earthquake, which we know that the largest earthquake in the last century is 9.5. But if you use a traditional surface wave magnitude, that was only 8.3. Likewise, Alaska, 1964 Alaskan earthquake is not, we know that 9.2 moment magnitude scale, but surface wave magnitude is 8.4. And in the 2 earthquakes in 1950s, Aleutian and Kamchatka, there again, surface wave magnitude is 8.25, but using the moment magnitude scale, that became 9.0. So Hiro showed that in his paper, there are 4 magnitude 9 or giant earthquakes occurred in the 20th century. And so again, the moment magnitude scale is based on the seismic moment. So seismic moment, we can estimate not only for seismic wave, but also like a geodetic data or tsunami wave. So after 2 years after the Hiro invented the moment magnitude scale, Professor Abe introduced tsunami magnitude scale, MT. And this is based on the tsunami amplitude recorded in the tide gauges. And Abe designed the tsunami magnitude scale in such a way that this tsunami magnitude becomes equal to the moment magnitude. That means we can use the tsunami data to estimate the moment magnitude. Then I use the tsunami waveforms recorded in the tide gauges to estimate to study the earthquake source. This is in a way similar to the seismologists use the seismogram to study the earthquake source. But seismograms contains information, not only the source, but also the earth structure and also the incidental response. And similarly, the tsunami waveforms and tide gauge records also contains information on the source and propagation path. But tsunami propagation is basically depends on the water depths. And water depths or bathymetry or ocean bottom topography is much better known than the earth structure. So we can reliably retrieve the information on the tsunami source. To do this, or to estimate, for example, the slit distribution or asperity distribution of the fault, I divided the fault into subfaults, and then give the unit slip amount on each subfault and compute the seafloor deformation and compute the tsunami waveforms. And using this as a Green's function, I just inverted from the observed tsunami waveforms to estimate the slit distribution. So the use of tsunami in like tsunami magnitude or tsunami waveform inversion, we started back in 1980s. Then the Wayne Thatcher and the USGS called it the tsunami wave seismology. Advantage of tsunami wave seismology is that we can use for the old events. So this slide shows Again, this is horizontal axis, the time of the year. It's 1810 to 1900 to 2000. And vertical axis is moment magnitude or seismic moment. Again, there are four giant earthquakes in 20th century. But right now, currently, we have very good broadband seismic data, but that is available only after 1980s. Okay? And before that, since 1960s or so, we have WWSN record, Worldwide Standard Seismic Network record. This is analog data, but it is very uniform seismic, the seismological system, seismic network system. But that is available only after 1960s. But for the tide gauge data, tide gauge records exist as far as back in 1850s. So we can use the tsunami waveforms recorded in tide gauge records to study such old events. So that's an advantage of this. Then to estimate the seismic moment, then moment magnitude to quantify the earthquake size. So this slide is the updated version of Hiro Kanamoi's the diagram. Again, this is a horizontal axis is the time from 1900 and 2000, and then this is now. Vertical axis is moment magnitude. And here shows that there are several earthquakes, few earthquakes in 20th centuries. After in the last the half century since the publication of the Kanamori paper, we had two giant earthquakes or magnitude 9 earthquakes in this century. That is a 9.1 2004 Sumatra Andaman earthquake and 2011 9.1 Tohoku earthquake. This just shows the list of earthquakes. It's magnitude 8.5 or large, more than 8.5. Okay? And then there's in terms of the moment magnitude. And there are 14 earthquakes listed here with magnitude 8.6 or larger. And you can notice that the 12 out of 14 occurred in subduction zone. Okay? So that generated tsunamis. And also, the last one is Wharton Basin occurred in the outer rise of the Indian Ocean. So that also generated a tsunami. So we can use that. So except for this continental earthquake, Assam, Tibet, all the others generated more or less a tsunami. And we can use that record to study those earthquakes. So today, I'd like to review or just show some examples of earthquakes. These earthquakes, like from South America, North America, Kamchatka in Japan, and in Indonesia. Okay. So let me start from not the most, but it's one of the recent earthquakes in 8.8 2010 Maule earthquake in Chile. So the 2010 Maule earthquake, Chile, that generated seismic wave, of course, but also this was recorded in geodetically. This shows the GPS data. The GPS network recorded several meters of the seismic displacement associated with the earthquake. And also, this earthquake generated some coastal uplift or subsidence that was confirmed by the field investigation. This just shows the uplift amount and also some subsidence. So that kind of geodetic data, both instrumental or field-based geodetic data can be and was used to study this earthquake. This earthquake also, in the 2010 Chile Maule earthquake, also generated a tsunami, and that was recorded Pacific-wide in the DART, which is ocean bottom pressure gauges. And shown here is the black line is the observed tsunami waveforms, and the red one is the simulated one, the modeled one. So if you look at this, near the source of the South America, the observed one, we can model we can reproduce the observed waveforms very well. However, if you go further, like in North America or in the Northwestern Pacific, you can see that the observed one is different from the model one. The model one arrived earlier, or in other words, observed record was delayed compared to the simulated one. And also, the initial motion shows negative phase, whereas near the source, there was only positive the phase. Okay. So when this earthquake happened, we didn't know why. So we could use only the near field tsunami data to study this earthquake. But after this event, in the last decade or so, we found that the reason for this delay, delay of the observed tsunami waveform, and that was due to the elasticity of the solid earth and compressibility of seawater and gravitational potential variation. I'm not going into the detail of this, but traditionally, when we model the tsunami, we consider the Earth as a rigid body for the tsunami propagation. Okay. However, when tsunami propagates, that has effect that just push this elastic Earth, and then just has a rebound. Okay. So you have to consider the elasticity of the Earth, or coupling between the Earth and seawater or ocean. Also, usually the seawater is treated as incompressible, but water has also some compressibility. So the elasticity of the water, also we consider this elasticity of the earth and water, as well as a gravitational potential variation. So if we consider this, the result becomes like this. This shows the dispersion curve. Horizontal axis period. This is 10,000 seconds, 1,000 seconds, and 100 seconds. And vertical axis is tsunami velocity. For the linear long wave, as I said, depends only on the water depth. And for the ocean, the constant uniform depth ocean, this is just a square root of GD. D is the water depth. So if this is water depth is 4,000 meters, then square root of the gravitational acceleration, 9.8 times 4,000 and square root. So the velocity, tsunami velocity becomes 198 meters per second. Okay. But we also know that for the shorter period, the tsunami is not really the long wave, but have to consider some dispersion or gravity wave. So for the linear gravity wave, velocity becomes like this. This is a function of the k wave number or lambda wavelength. So the shorter wavelength becomes slower. So this is just the dispersion curve for the linear gravity wave. But if we that has been known for many years. But if we further consider the elasticity of the earth and water and gravitational potential variation, the dispersion curves also, tsunami velocity also becomes slower at longer period, like this. Okay. And also, mostly because of the complexity of seawater, this just a maximum is slower than the linear long wave. So this is why the observed waveforms in like North Pacific or Japan from Chilean earthquake arrives later because it is slower. And also the waveform, the initial negative phase is produced by this dispersion. The different velocity depends on the period or wavelength. And this difference is about, you can see this one is 195 and 200. So this each tick is 1 meter per second. So it's about 2 meters per second slower than the linear long wave. So that is about 2 over 200 is about 1%. So if you consider this effect, the tsunami velocity is slower than about 1% than the linear long wave or linear gravity wave. And 1% is usually not very visible, but for such a tsunami in long distance, that becomes very visible. Okay. Actually, let's see. If you consider this effect, that a tsunami waveform from Chile, Maule earthquake, recorded near Kamchatka, became like this. This one is, I already showed this earlier. And black one is observed. And by considering these effects, we could reproduce the waveform, initial negative and also a delayed arrival, as shown in the red curve. which is later than the blue one, which is from the long wave or linear long wave theory. And likewise, from Tohoku earthquake recorded off Latin America, also we could reproduce the initial negative phase and also the delayed arrival compared to the long wave. And again, this one is like from Chile to Japan is almost 20 hours. Okay? So 1200 minutes. So 1% of this is like 12 minutes, right? So then for such a long distance or propagation, this delay, 1% delay, is become very visible. But now we know that we can use this effect to model this. Okay? So by using this, considering those effects, the Maule earthquake, the distribution can be estimated from tsunami data. Well, also we use the geodetic data. But before that, as I showed earlier, if we use only for the near field data, the slip distribution was like this and somewhat closer to the land. However, if we consider this, those effects, the slip becomes offshore and the larger patch in the north becomes larger. And this result is very similar to other results, like seismic waveform, P and SH wave, or GPS and INSAR data, and INSAR and tsunami, and also seismic GPS and INSAR. All of them show that northern asperity of the offshore. Even if we use only for the far field tsunami data, we can reproduce, we can just estimate this distribution. But for the 2020, we have many data, seismic data, GPS, and INSAR. But all the earlier, older event, as I said, we don't have such good data, but we do have some tsunami data to estimate the source. So let's move on to the Chilean earthquake, 1960 Chilean earthquake. For this event, we have, as I said, we have limited seismic data, but using some limited seismic data, we can estimate for the, we can use this as a long period surface wave, like a G2, R2, Rayleigh wave, lava wave, Rayleigh wave, circling around the Earth a few times after the earthquake. And here Kanamori estimate this using this old data. Then actually this is a strain meter, but they use this strain meter, and then estimated moment magnitude is 9.55 plus minus a quarter of magnitude scale. Our moment magnitude, seismic moment is about 3 times 10 to the 23rd. Using the geodetic data, this is coastal, again, this is coastal uplift subsidence. Also, there's some leveling data. And using those geodetic data, several people modeling this, and this is one of them. And the seismic moment becomes about 1/3 of this, or moment magnitude is 9.3, 0.3 or 0.2 or 3 moment magnitude scale unit lower than the seismic estimate. If we add tsunami data, the slip distribution is also similar. But again, the seismic moment is 1.3 times 10 to the 23rd, or moment magnitude is 9.3. So these are actually the geodetic data, the tsunami data show the smaller seismic moment. Okay. And this is a kind of unusual diagram showing the horizontal axis is publication year of the paper result, and vertical axis is moment magnitude scale. So soon after the earthquake, the earlier studies using the geodetic data estimated about 9.1 or 9.2 in moment magnitude. Then the geodetic data, like the Barrientos world or Moreno et al., which I showed it, shows that less than 9.3. If we add tsunami data, still up to like a 9.3 or so. Whereas seismic data, either free oscillation, mostly free oscillation data, and also strain meter, shows the moment magnitude larger than 9.5. So there's some discrepancy between the seismic estimate, geodetic, and tsunami estimate. But in either way, Oh, so I have to say that, well, in this region, there's some early earthquakes before 1960. There's 1837, 1737, and 5075. So the average recurrence interval is like 125 years or so. Okay. But for the most recent event, I should have explained that for the largest slip is about either from tsunami data, geodetic and tsunami data, or geodetic data. You can see that the largest slip is more than 20 meters here. It's shown here in this scale, or here on this color. Okay, so the largest slip is more than 20 meters. So then for this here in this region, this is kind of earlier papers, but the convergence rate is about 10, nearly 10 centimeter per year. Okay? So if this is 10 centimeter year, and if the average recurrence interval is 125 years, that you expect like 11 meter slip, right? However, the 1960 was 20 meters, as I showed earlier. So slip is too large, or maybe interpret earthquakes is too often. So then, again, this just shows the earthquake, the historical evidence: 1960, 1837, 1737, and 5075. Again, to average of 125 years interval. And all of them show some evidence of tsunami and also the coastal displacement. Okay. But recently, later, my colleague showed a study from tsunami deposit. And this is in picture from the outcrop in Maojin, in South region, here, Rio Maojin. And top one is the tsunami deposit from 1960. And there are several earlier, older tsunami deposits found in this outcrop. So then they dated. And then what they found is, of course, the top one we know that 1960. And the second one is not 1837 or 1737, but corresponding to 5075 using the radiocarbon dating. And then the third one is around 1300, and fourth one is around 1100. So interval for this tsunami deposit is about 300 years, which is longer than the 125 as inferred from historic data. So what this indicates is not all of these earthquakes in historical earthquake produced, not all of them are large enough to produce the tsunami deposit. And only 1960 and 5075 are large or giant size to produce the tsunami deposit. So there's some hierarchy of the earthquakes in this region. So we looked at in South Chile, southern Chile, and found that magnitude giant earthquake occurred in 1960 and 5035, but 1737 and 1837 was smaller, still, great earthquake, but not giant. And similarly, in the region in 2010, Maui earthquake region, there's a similar event in 1835, more than 150 years ago, before 2010. And so this just shows some giant earthquakes are not as frequent as like historical document indicates. Okay. So that's Latin America. Then let's move on to the North America, Cascadia subduction zone. So Cascadia, we know a lot now, but when like 87, actually when I did my postdoc in Caltech in 1980s, when I arrived there, Tom Heaton showed this picture, and he compared the southern Chile, Cascadia, Nankai, and these are all tectonically similar subduction zones. All of this is young plate is subducting. And in southern Chile, as I showed, that 1960 Chilean earthquake produced like about 800 kilometer the south region. And we know that Nankai, the large earthquake occur, whereas in Cascadia, there's no evidence of such a large earthquakes. But in the last 30, 40 years, since 1980s, the geologists, paleoseismologists in North America, like Brian Atwater, found some evidence of past earthquakes. Like here, that show the coastal geology showing dune sand then on top soil. So these are deposited above sea level. Then on top of this, you have tsunami sand and tidal mud. They are deposited below sea level. Okay? So this indicates there's some subsidence event in the past. Also, the trees, these are the ghost forest. And these are like this. When the trees are here, then his coastal area on this forest region is subsided, then intruded by the tidal water or tsunami. Then those trees are died, then standing dead like this, ghost forest. And also the tsunami deposits may be recorded or some liquefaction, they are evidence. These are the evidence of past earthquakes, past subduction zone earthquake associated with the crustal deformation. And using this paleoseismological data, they estimated that the most recent event occurred about 300 years ago or 1700. Okay. But, well, the 300 years ago or 1700 is a prehistorical time in North America or Pacific Northwest. However, this is a historical time for us in Japan. So if this earthquake is large enough to produce the trans-Pacific tsunami, that may be recorded in Japan. And we looked for some Japanese historical documents and found evidence of tsunami or documentation of tsunami. And some of them indicate that tsunami came without earthquake. And also they recorded the time of arrival. That is January 27 of the 1700 in Japan time. So using this tsunami documentation and using the computer simulation, we could estimate the size and also the time of the earthquake in 1700. And that is January 26. And earthquake size is about 1,100 kilometers long, and slip is more than 10 meters. Moment magnitude is 9.0. And although this is not our work, but it's just the Brian Atwater and paleoseismologist indicates that the similar the recurrence interval estimated from the paleoseismic data is about 500 years. So let's move on to the North Alaska allusions. Here, I'd like to briefly mention about 1964 Alaskan earthquake and 1957 Aleutian earthquake. 1964 Alaskan earthquake, from aftershock distribution or body wave analysis have been done. Then also some geodetic data exists. Then we also use the geodetic and tsunami. And then estimated, and also more recently, well, still to about 10 years ago, but the joint inversion of geodetic, tsunami, and seismic data has been done. And they all show that moment magnitude is about 9.1 or 2, kind of a consistent result. But they also show that there are two asperities in Prince William Sound asperity and Kodiak asperity. First proposed by from the body wave analysis, Doug Christensen and Susan Beck. But also the later geodetic data, tsunami, and inversion also show two asperities. Okay? Then for the paleoseismological work in this region has been done, and they show that like in Kodiak Island, in the Kodiak asperity region, there's many evidence of the earthquakes in the past. Sorry, Kodiak is here. There's several evidence of the past earthquake. And penalty event or the last event occurred about 500 years BP. And recurrence interval varies, but it's roughly speaking about 500 years for this such a giant earthquake in Alaska. Well, Aleutian, 1957 Aleutian earthquake. This one has a very long aftershock area, like 1,200 kilometers long. So based on the aftershock area, the length and width, Hiroki Amori estimated like a moment magnitude 9.1. And then he put this one is one of the giant earthquake in 20th century. But later we use the seismic, limited seismic data, like a surface wave, record here. And then just shows that moment magnitude is smaller, like 8.4. And we use tsunami waves, and it also shows some smaller moment magnitude is of 8.6. More recently, the far-field tsunami and near-field tsunami evidence was modeled by Yamazaki et al. And they also show that moment magnitude is about 8.7, 8.6 to 8.8. So now this is no longer giant earthquake, but still the great earthquakes occurred in the 20th century. And Yamazaki et al. Also used the tsunami data, period tsunami data, and the penultimate, then this one just the earthquake evidence of the old event, both in Aleutian and also recorded in Hawaii. And they dated, this is the penalty event, the older event is occurred about 500 years ago, and size is similar. So again, the similar giant earthquake occurred in the past earthquake occurred about 500 years ago. But then, if you go further west to the Kamchatka, there's a large earthquake, giant earthquake occurred in 1952. And this one, we modeled this one earlier and using the tsunami data, and then estimated the slip distribution is like this, rather deep in the subduction zone. Okay. But using the near field data, the Magnus et al. That's proposed that the slip must be in shallow region, or shallow slip can better explain the near field tsunami height. And here, as you know, that we had similar earthquake in last year, and that was recorded. It also produced a tsunami, and now we could use the tsunami data recorded around the Pacific Ocean. Okay. And then based on this tsunami data, we estimated we did inversion of that on tide gauge data, and slip is like this. So the epicenter is here, but the largest slip is to the south, about 200 or 300 kilometers. Each subfault this is 100 kilometers, so about 300, 400 kilometers south of this. And then the moment magnitude is about 8.8, and maximum slip is about 10 meters, okay, using either that or tide gauge data. But if you compare the tsunami waveform from 1952 and 2025, they're very similar. Shown here in black is the 2025, and green is 1952. So you can see that the waveforms are almost very, very similar in Japan, or this one is for the South America, except for the Hawaii. Hawaii, the tsunami 52, tsunami is larger, like in Hilo or other, the other islands in Hawaii. Okay? And based on that, on those records, we could estimate the distribution of 1952 Kamchatka earthquake and compare with the 2025. Roughly speaking, they're similar, but if you look at some details, there's some slight difference, particularly this because of the Hawaiian record. That causes the tsunami wave propagating in this direction toward Hawaii. By using those, the slip distribution is slightly different. And in 1952, it's slightly shallow. The maximum slip is shallow region, whereas 2025 is slightly deeper than 1952. And also, the maximum slip is larger in 1952. But the question is, there's only 73 years between 1952 and 2025, only 73 years, and such a large giant earthquake happened. The 73-year interval is much shorter than what we have seen in South America, North America, and Alaska Aleutian, right? But in this region, if you look at the historical data, there are also earthquakes in 1841 and 1737. And this Russian colleagues published a paper in that they show that recurrence interval of magnitude 9 event is about 84 to 100 years. This one was published before 2025. Okay. So that in this region, the magnitude 9 earthquake seems to happen in more frequently than other subduction zone. But how about for the comparison is convergence rate? Here, the convergence rate is about 8 centimeter per year. So that is about 8 meter per century. And as I said, this is only 73 years since the last event. So the cumulative sleep will be like 5.68 meters, which is smaller than 9 meters. But this can be explained, the difference in the largest sleep location. 1952 was the maximum sleep was shallower than 2025. So in other words, in each event or 1952, not all the accumulated sleep strain has not been fully released. So that's why we had a larger sleep in 2025 than expected from the convergence rate. If you look at some geological data, the Russian colleagues also studied the tsunami deposits in this region. And they found that many tsunami deposits, and this about 30 tsunami deposits or 30 events in the last 4,000 years. So this also indicates like 130-year interval. However, they also show that some different kinds of the earthquake, that is not only tsunami deposit, but also some coastal associated with coastal subsidence. And such event occurred only 3 in the last 4,000 years. In other words, then the recurrence interval is like 1,300 years. So there seems to be even larger or different kinds of earthquake occurred in this region with a longer interval than this magnitude 9 event. So then go to Japan. Here I'd like to show that the 17th century earthquakes in offshore Hokkaido and Tohoku region in 2011. In Hokkaido, we have magnitude 8 earthquakes in 2003 Tokachi-oki, 1952 Tokachi-oki, and 1973 Nemuro-oki, 1894 Nemuro-oki region, 1843. Slightly different region, but it just all of it is magnitude 8. But we found that in 17th century, there's a larger earthquake occurred in this region based on the tsunami deposits. So we studied this one in Kirtap Marsh here in Hokkaido. Actually, I should say that Kirtap is here. Kirtap Marsh is here, okay, in this region around here. And here we know that the 1952 Tokachi earthquake or 1960 Chilean earthquake produced a tsunami and flooded or inundated about 1 kilometer from the coast. But when tsunami deposits are shown here, sorry, this one, like the sand layer, extended further inland in a few kilometers, several kilometers from the coast. And such a sand deposit or tsunami deposit, then we also have a volcanic ash layer. And we know that where and when the volcanic ash layer comes. And then based on this one, for example, the volcanic ash layer, light color, it occurred in 17th century, that is 1739, 1694, 1677. Okay. And below this, we have a BTM. This is a Bektosan Tomokomai, occurred in North Korea. That we know that AD 946. And between these volcanic ash layers, there are 2 sand layers. And below this is we have another volcanic ash layer about 2,500 years ago. And between this and BTM, Tomokomai, and Bektosan Tomokomai, there are 3 to 4 layers. So based on that, we estimated the recurrence interval of such a tsunami deposit is about 500 years. And then we model this to model. So this one is just a tsunami deposit distribution. To reproduce this, we tried several kinds of fault, like a tsunami earthquake or giant fault or typical interplate event. Then we found that the interplate event with larger sleep, but for the multi-segment, then the 10-meter slip in Tokachi, 5-meter slip in Nemuro region can reproduce this tsunami deposit distribution. After 2011 Tohoku earthquake, Ioki and Tanioka, they combined this model and tsunami earthquake model, the larger slip on near trench axis, to better explain the tsunami deposit distribution. So, but this model is 8.8, nearly the giant earthquake size. Then also the more recently that after then we just studied the tsunami deposits more systematically, and then this one there are like 16 layers in about 5,000 years. And then this just shows the interval of between each tsunami deposit. They varied from like 100 to 800 years, but on the average, this is about 400 years interval. So now we believe that the magnitude 9 giant earthquakes in this region, recurrence interval is about 400 years. Then Tohoku earthquake, I'm just running out of time, but Tohoku earthquake, remember that that produced a huge tsunami, and that was recorded in offshore at bottom cabled pressure sensors. And this shows the gradual rise and sharp rise, and that is recorded here, then just propagated toward the land. Okay. And to reproduce this, we need two kinds of slip distribution. One is, so this one is two stages, slow gradual rise and sharp rise. Okay. And if we model this with the typical interpolate event, like H69 type event, then that can reproduce the first initial rise of the water, but cannot reproduce the sharp secondary tsunami with very sharp rise. And tsunami earthquake type can reproduce the very sharp rise later, because this is offshore, but not for the first gradual rise. To reproduce the tsunami waveform, we need to combine the interpolate event type and tsunami earthquake type. And so this one is for the Tohoku earthquake, but how about for the older event? Again, here with the tsunami deposits have been studied, and then top one is 2011, and we know that I already mentioned that H69, but there's an earthquake in H69, Jogan earthquake, and that is layer 8. But between this, above this volcanic ash layer of 915, there's another tsunami layer of layer 4. Okay. And historical data indicates this corresponds to either 1454 or 1611. We are not sure which one is this. But if this is 1454, the interval is about 550 or so, 571 years. And if this is 1611, then this one is longer, and this one is shorter, but average is, of course, is same as 571 years. So finally, we go to Sumatra and Andaman, and we know that this earthquake happened in magnitude 9.1 or 2, and then here again we have 2004 tsunami, and then also there's some tsunami deposit on older event, about 500 or 600 years before. Then similar tsunami deposit has been found in Sumatra, and then this shows some earlier tsunami deposit, tsunami. This kind of work was done in the last 20 years in Thailand, Sumatra, and Nicobar, and also the Indian coast. And they also show the older event. But all of them, dating is not really consistent. That is, some places shorter, some places slightly different time. But more recently, there's a tsunami deposit study also done in Africa, and they show that the penultimate event was like AD 950. And this dating is consistent with some other region, Thailand, Andaman, India, and also. So the similar earthquake to the 2004 may happen about 950. That is about 1,000 years ago. The interval is 1,000 years. So to summarize this, we have looked at Southern Chile, Cascadia, Alaska, Aleutian, Kamchatka, and Kuril, Tohoku, and Sumatra Andaman. All of them shows the magnitude is about 9. And the recurrence interval is about 300 to 500 years, except for the Kamchatka, which is shorter. So, to conclude, the geophysical, seismic geodetic tsunami data, quantified size, moment, magnitude, length, maximum slip of giant earthquakes, and five events of magnitude, moment, magnitude 9 have occurred since 20th century. And historical geological studies show that the penalty events occurred a few to several hundred years ago, and seismological studies show that giant earthquake occurred in other subduction like Cascadia, where we have no mostly more recent data, but yeah. And the recurrence interval of Kamchatka is significantly shorter than other subduction zones, but seismological study implies that more giant or different kinds of earthquake with longer interval. That's all. Thank you.
Thank you, Kenji. Thank you very much. We can now open the floor to questions, starting with a question from Kellen Wang. 2011 Tohoku is widely quoted as magnitude 9. Can you elaborate why is it shown as magnitude 9.1 in one of the slides?
Oh, that's from USGS. I don't know why, but USGS list shows 9.1. So I just, for the list, I just adopted from USGS. How do I see the Q&A?
I'm not sure, but I can read them to you. That's
okay. Okay.
Another question from Daya Shankar. Our inundation height effect depends on the coastal geometry.
Yes, of course. But the coastal geometry, I assume the coastal geometry hasn't changed, except for the artificial construction, like a breakwater. But the basic, coastal, the coastal geometry or topography hasn't changed in the last few hundred years. Well, the coastal line may change because of the sea level change, but for the coastline may have changed, but not for the coastal topography in the regional scale.
Thank you. Any other questions? You can type a question in the chat or in the Q&A box. Looks like your presentation was crystal clear, Kenji.
Okay.
Ah,
I'm looking at some.
another question from Killian. Thank you for the wonderful talk. The magnitude of some of the historical events at Kamchatka seem to be controversial. Can you discuss that?
Well, yeah. Yes, this one. Actually, to quantify the old events, for the old events, the size of old events like 1737, 1841, are based on the ground shaking intensity in Kamchatka, but also in tsunami, far-field tsunami. And this just shows I actually I prepared this one. I didn't explain that this table shows the tsunami height in Kamchatka and Hawaii. And that really varies. But in 1737 is like a 3 to 9 meter in Kamchatka. 1841 is 1 to 15, 1 to 23, and up to 19. So kind of similar in Kamchatka. Also in Hawaii, although that old one is very varied from 1 to 15 or 4.7 or 5.7. But in that is, well, roughly speaking, they're producing tsunami recorded in both Hawaii and Kamchatka. So I believe that they are in kind of similar size.
Another question from Jose Gonzalez Alfaro. What could be the main factor that would control the mega earthquakes recurrence for different subduction systems?
Hmm? What is the main
It's
factor?
it's in the chat.
Oh, what could be the main factor? This will control the mega surface ground. I don't know what to control the mega recurrence for the different subduction system. Well, but I show that at least except for the Kamchatka, the recurrence interval of giant earthquakes seem to be similar, and that may be related to the convergence rate. And so the main factor to control the megasurf. Yeah, right. So that is basically the size of earthquake and convergence rate, and that is kind of common feature, I think. That I don't know if I answer the question.
Um, let's see. We have another question from Marino Proti. Thanks, Kenji. Can local submarine landslides induced by large subduction earthquakes complicate the tide gauge and tsunami deposits inversions?
That's true. That's true. The tide gauge, we can just the local the landslide has a different feature in terms of tsunami period or waveforms, and also the deposit may be kind of local height. That of course amplify the tsunami height, local tsunami height, and also the deposit, but the local submarine landslide, its effect is usually limited in terms of the geological, the geophysical, sorry, geographical, extent. So if you have some unusual, for example, like a Kamchatka, if you have some unusual, height, unusual large one, that may be effect of the local, submarine landslide. But typically, this is very limited in region. Like 1964 Alaska also produced multiple landslide, local landslide, but that effect is kind of limited in geographically.
And then I think we have time for one more question from Rachel Abercrombie. Just curious, what are the current major challenges or uncertainties for modeling new tsunamis?
Well, for the new tsunami, then that we have very good. You said new tsunami? What did you say?
New tsunamis,
Yeah.
yes.
Well, we have very good, the Pacific-wide ocean bottom pressure gauges, and that are recorded very, very well. And uh, if you have time, I think we can just reproduce very well. And like a Pacific, so the challenge may be how to utilize this, or how we forecast or utilize this for the tsunami forecast or tsunami warning, right? For the Trans-Pacific tsunami, we have enough time. So now we can analyze the seismic data, geodetic data, and yeah, on real time, and then predict the tsunami waveform or Trans-Pacific tsunami waveform very well. But for near field, that the tsunami arrival is very short. So it's to make a quick tsunami warning. And also that may also local tsunami may be affected by submarine landslide, as some previous person asked. So the forecasting that near field tsunami or utilizing this for the tsunami warning may be still a challenge, I think.
Thank you. And I think that concludes today's webinar. I would like to thanks one more time Kenji Satake for taking the time to present for the SE for the International Webinar Series. I wish you all a fantastic day or evening and hope to see you soon for another SE4D event. Thank you,
Okay, thank you
everyone.
very much. Thank
Thank
you.
you.
Yeah. Okay. Bye.
Bye.